This is lesson 20, and it's on operational amplifiers. So this is somewhat different than what we've been talking about, but an operational amplifier has it's a differential amplifier, and it amplifies the difference between two inputs. The book talks a little bit about this, but not a lot, and not a lot of detail as to what's actually inside this little operational amplifier that we're going to look at in a little bit. So mostly what we're looking at in this lesson is how can you use it in various circuits to do different things. And there's 4 circuits that we're going to look at. What I'm basically going to do, I need to show you what's called the pin out list for the operational amplifier, and then I'll show you a circuit. We'll actually go to the circuit board and I'll show you on there how you connect everything and what you need to look at on the oscilloscope, and then I'll come back and we'll look at the other circuits. And I'm not going to show you everything that you're going to see on the oscilloscope. I'm going to leave it up to you to see what you can discover. But as usual, if something doesn't look quite right, please let me know and I'll help you figure out what you're doing wrong, if anything. Okay, the first thing is that we're going to draw the symbol for and the abbreviated op amp, so not so many syllables. It looks like this, and we'll look at one in a little bit, but they're only like a centimeter long and maybe, I don't know, they're really small. Okay, so they have pins on the side, and there's 4 on each side, and those pins go in the holes on the circuit board. So this is 1, 2, 3, 4. When you look at the top view, you're looking at the black, and the number is usually up here somewhere, oriented some direction. There may be other things besides just the number. The 741 is a very popular one, and that's what we're going to use. There's a little dip here, and then also in the upper left-hand corner there's a dot. So there's several ways for you to tell if you're holding it correctly. Okay, and then we have on the other side, we have 4 pins. So we start at the upper left-hand corner and just go around the outside. So we have 1, 2, 3, 4. This is 5, 6, 7, and 8. I'm not going to write what these are because I have those listed. There's a few of the pins that you don't use, but the ones that we're going to use all of the time. And what I've tried to figure out is in our circuits, so that we change as little as possible, and instead of redrawing, you'll have to redraw it, but when I do it, I'll just change a little bit. So inside of this, what we're going to look at is the standard diagram of an operational amplifier. And it's a triangle that has a minus up here and a plus here. In one of the sections that I've listed for the reading, he talks about what these pluses and minuses are, and there's basically 2 sides and with some transistors. I don't think I'll get into much more than that. But anyway, we have a minus here, a plus here, and these are inputs, and then over here on the right, this is an output, and then we also have to connect to another voltage. So this goes to pin 2, the plus goes to pin 3, and then we will end up connecting things out here to these pins. Pin 4 goes to this position, and there's a voltage that this will be attached to. And then pin 7 is another voltage. This is actually a positive voltage and this is a negative voltage. If you notice over there the labeling for pin 4 and pin 7. And then pin 6 is the output, and we generally draw a line like that. So pins 2 and 3 are the input. Pin 6 is the output. Pins 4 and 7 are voltages that are maintained to have the operational amplifier to work properly. Okay, so you should draw that on page 163. Okay, now we're going to go to the basic inverting amplifier. So I'm going to draw the circuit over here, and I'm going to draw it so that when we do the other circuits, that I'm going to change as little as possible. So notice I have our triangle here with a minus up here, a plus down here, and what we're going to do is the voltage that is maintained at those two pins is minus 12 volts and a plus 12 volts. It's normally the same voltage. It doesn't have to be 12. It could be something in that vicinity. I suppose if we wanted to do 15, that would work also. But these circuits are ones that my husband had used in his class when he did this before. I kind of redrew some of the diagrams, some of the circuits, so they were a little bit more consistent with each other. Okay? Then we're going to go over here and come down, have a resistor. This goes to ground. There's two grounds. They're actually connected inside that you know. There's one in the upper right hand corner. It's labeled GND with a black terminal. And then in the lower left hand corner is the ground that goes with the function generator, and it's connected to a BNC terminal. Okay, this is the load resistor, RL, and it's a 390 ohms, and that one is an orange, white, brown. Okay, and then since this is the output, we're going to look at channel 2. We're going to have channel 2 as the output, and we're going to connect channel 2 to that side of the resistor. Okay? Now, this positive side here, we're going to go to ground, and I'm going to call it the BNC ground. Okay? Actually, these are the same thing inside, but it just looks better to have this one connected to the BNC ground. Okay, then over here we're going to come out. We have a resistor, and then we're going to have our input. On some of these we're going to have a sine wave input. There's one that will have a square wave and one that we will have a triangular wave. But this one, it's VN. And we're going to connect channel 1 right here. Remember that when you use channel 1, generally you put the hook one place and then the ground of that same probe goes someplace else, and so we'll have it connected down here to our BNC ground. This is R1. It is a 2.2 kilo ohm. A lot of times we don't go ahead and put the ohms. Notice I didn't put it here. It's just kind of a convention that it's easier to leave off the symbol ohms. So this is a red, red, red. And then we have another resistor that goes here and up and across and connects down over here. So this is R2. And it is a 10 kilo ohm resistor, which is brown, black, orange. Okay, so this is the circuit that you should be drawing in step 1 on page 164. Now, the next thing it does, actually over here, I need to put V out. It says label the positions of the needed pinouts, and that's the standard terminology. So this negative is always pin 2, and I assume by the time you do a couple of these you'll kind of know what they are. I kind of go in order. This is pin 2, this is pin 3, this is pin 4, we don't use 5, this is pin 6, this is the output, and this is pin 7, and we don't use 8, and we don't use 1. Okay, so that has that's the circuit with all of the pinouts labeled. Okay, I think that's what I need to show you at the moment on the board. I'm going to go now to the circuit and show you how to connect all of this and what you're going to be measuring. Oh, wait a minute, before we do that, one thing on all of these, I have you to draw what you see for channel 1 and channel 2. You're going to look at channel 1 first, and then channel 2, and then dual, where you can see both of them at the same time. And I said draw these reasonably to scale. So, and some of the things that I've said reasonably to scale haven't been quite as much to scale as I would have liked. So what I would recommend is that you have a graph. You can draw it freehand. You don't really have to have a ruler and measure. But if you're going to have a voltage of, say, 2 volts and 8 volts, no, 2 volts and 6 volts, and that's not quite what you'll have, so I'm purposely using some other numbers. So we might say 2, 4, 6, 2, 4, 6, and if we have a sine wave, and it does tell you to adjust the sine wave so that it starts at the origin. So if we have a 2 volt sine wave, and I say to sketch this for 3 cycles, so I need 6 of these, 1, 2, 3, 4, 5, 6. So I would have 2 volts here, about here, something like this. That's not, I spread that out too far. Okay, so I have here, kind of down, here, something like that. And then if we had something that was 6 volts, then it should be up here, and so on. So these should be reasonably to scale. And I think when you see the graphs, you'll see why you need to have them that way, so you can tell a little bit better what you actually have. Okay, let's go to the circuit. And let me turn the oscilloscope on. We see a wave there already. Okay, so let me explain a few things about this. The little black thing here is the operational amplifier. So at some point on the top it should say 741. Where's the 741? I get it right side up. So it looks like this on the top, and then it looks like this on the bottom. Actually, it looks like a bug that's lying on its back with its feet in the air, kind of. And you notice that it has 4 pins on one side and 4 on the other side. So that needs to go into the circuit board. Now, notice that I have it straddling this little groove here. So you cannot put it like this, because these pins are all in the same row, they're all connected, and so that's not going to work at all. So it works nicely, and come to think of it, that's about the only place you can actually put it, is straddling one of these grooves. So it doesn't really matter. But I figured out that you need to connect some things over here to the function generator and some over here to this side, so it's best if you have this kind of in the middle. And you may need to actually cut and strip some more wires. I sent a number of wires, but you may not have enough long ones. So, okay, so you get that in there. Make sure, let's see, okay. Now this one does not have a little dip at the top. It does have a dot. Actually it looks like the dot is about in the middle, but that should be at the top. So it's kind of important that you have it oriented properly. Okay. So then our first hole is pin 1, which we don't have anything for. Pin 2 is negative, and on our circuit on the board and that you just drew, that needs to go to resistor 1, which is the 2.2 kilo ohm, which is the red, red, red. So I've got the red, red, red in the same row as channel, or as pin 2. Now I've moved it over a little bit. I've left a space because you notice that the 10 kilo ohm resistor also needs to go in the row with pin 2, but it goes over here to this other side. So I put it closer and then put the 2.2 a little bit farther out, and then you just put it somewhere up here. Okay, that's pin 2. Now pin 3 is the one right next to it, and it goes to the BNC ground, which is over here, so that's why I have this one. Pin 3 goes over here. Pin 4 goes to the minus 12 volts. It's important, and it does tell you in here that you adjust both of these, the yellow and the blue, to the 12. One's plus and one's minus, so you use the voltmeter and connect to this ground and the yellow, or this ground and the blue, and adjust it to 12 volts. Now, it doesn't have to be 12.00. It usually won't stay quite like that, but very close to 12. Okay, so pin 4 goes to the negative. So I've got pin 4 over here, and this black wire going up here to the negative, which is the blue terminal. And then pin 5, starting on the bottom right, doesn't go to anything. Pin 6 goes to the output. It goes to our load resistor, which is the 390 ohms. So I've got it in the same row as pin 6. And then the other end of it is just down here, and then that has to go to ground, so I've got that going to the black ground up here in the upper right hand corner. Then the 10 kilo ohm resistor, as I mentioned, it goes in with pin 2, and then also over and into pin 6. You have to remember it starts 1, 2, 3, 4, and then 5, 6, 7, 8 goes up the other side. I've got those mixed up a couple of times. So it goes from the left side pin 2 to the right side pin 6. Okay, so I would connect all of those, and then our resistor 1, this one, we're going to connect our input, our function generator, set at 1 kilohertz. So I've got it up here at the 1K, and then also be sure the knob is turned all the way to the left for the sine wave. Be sure that this one is turned reasonably to the right. I don't think it matters exactly if you have it 1000, but if you want to adjust it, you can actually use this meter and adjust it, or and I think it's in, I don't know, one of these lessons. If you put this, and I changed it to 0.5 instead of 1. If it's on 0.5 milliseconds per division, and then if you move this sideways, then you can see that from peak to peak sideways is 2 centimeters. If you have this on the 1, then it's 1 centimeter, but I think 2 spreads this out a little more, and it's easier to see some of the later waveforms that you'll be seeing. Okay, so that's adjusted the frequency, and then you need to adjust the amplitude to 1 volt of amplitude, which is 2 centimeters peak to peak. So this is almost that, so I will take my amplitude here, and then you have to adjust. Be sure this is on channel 1, and I've got this on 1 volt per centimeter. When you're doing these, it's certainly fine to change some of these, the scales, so that you can see the graph a little bit better. The only thing you want to really make sure of is, and there's a note in there that says this, that when you're looking at channel 1 and channel 2, you should have both of these on the same range, because the idea is to see how one of them, how big one of them is relative to the other, and if they're on different ranges, then it's not that obvious. Okay, so I still need to get this to be, okay, that looks good. That's about 1 volt peak to peak, and then we're going to move this over so that the sine wave starts at the origin. That's what I mean by that. Because you're going to be looking at the input and the output wave, and you want to be sure that you can tell what the output wave looks like relative to the input wave. So if you just start the input wave, which is channel 1, always where it crosses there at the origin, then you'll be fine. Another comment is that when you are doing the other circuits, you think you won't have to change this amplitude, but based on what happens in this circuit, they don't always stay at 1 exactly, and it's going to work best in your calculations and in the analysis if your input really is 1 volt amplitude. So if you have to change that a little bit from one circuit to the other, that's fine. Okay. Now, let's look at something else. So this is channel 1. Now, if you want channel 2, make sure that you move this to channel 2. And it's like, oh my, that's very tall. So it's kind of off the screen. So that means that you're not going to very accurately be able to tell what that amplitude is. So that means that on this division, or on this scale, you need to move this one down to whatever that is. Is that 1 or 2? 2 volts per centimeter. And if you move this one down, then you need to move that one down as well. Now, you can't see that because I don't have it on channel 1. So there's back to channel 1. Okay? Now at the bottom of 164, I have sort of blanks for you to fill in, because I want to see what numbers, and people have a tendency to not write down as many numbers as I would like. So I put blanks for you to fill in. So for the input voltage, that's how many centimeters. So if you measure this, I've got about a half a centimeter times how many volts per centimeter. So on both of these, I have 2 volts per centimeter, and then that equals whatever the voltage is. Okay. Now over to the right, I also have for you to measure the voltage using the DMM. So we're going to look at that. Now, we're going to measure the voltage from the function generator. Remember, the function generator is an alternating current, so we need to change our voltmeter up to the 20 volts AC. So that's the voltage with the little wavy line. So I might as well turn that on. And then it doesn't really matter which way you measure this or which side you put the black and the red. And I'll just hold it because I'm missing my alligator clip off of here. So if I want from this ground up to where my channel 1 is, I can either connect it there or I'll just go to this end. And my arm is in the way probably, but it's 0.66. So you're going to record that. And then also the output. So that's going to be just, where do we have that? Oh, it's probably from this ground, it's across this resistor, so let me try that. That ground goes up there, and this one goes here. And I have about 3.07, and that's just a tiny bit different than what I had before, but it's about right. Okay, so that's how, or if you've got the alligator clip on here, just clip across this resistor. Okay, so then on the next page, you're going to draw the graph. So this is where I was talking about drawing reasonably to scale. So if you have this, and then notice channel 2, and I want to point this out because I'm not going to point anything out on the others. I'm going to let you do those. I'm not even going to show you the what you get on the oscilloscope. Notice that this is pointing down when that one's pointing up. And the easy way to tell that is if you go on down to dual, it shows you both of them at the same time. And so that is what your graph should look like. It should have this one as fairly small, it should have the output as large, and it's inverted. So that's, you could probably have figured that out from the name of this because it's an inverting amplifier. So that's not too surprising. Okay, then there's some more questions about voltage gain, and there's an equation in the book which I decided not to derive. I even gave you the equation, I told you where it is in the book for the voltage gain based on the resistors. And there's a few more questions there. There's also a question at the end about how could you have predicted the DMM values from your voltage, the V in and V out that you measured on the oscilloscope. And I referred you back to lesson 8 because you did a lot of this back there. Okay, so most of these others are almost the same. So I'm going to go back to the board. I'm actually going to turn this off. And we'll go back to the board. There are some things I want to mention about some of these others. The next one is the basic non-inverting amplifier. So it should not be a surprise if your output is not inverted. I guess it should be a surprise if it is, because it shouldn't be. Now, we need to draw the circuit. So you have a big blank page or spot there. So what I'm going to do is to show you how you can take what we have here. Basically, I'm not going to erase anything unless I really need to. So I have to pay attention to my circuit that I drew here. So I'm going to start with the operational amplifier. And if you're drawing this, this is usually where you start, with the operational amplifier, minus at the top, plus at the bottom. Output to the right goes over down to the load resistor and to ground. It has a negative voltage out here, a positive out here. We're going to keep those both at minus 12 and plus 12. It has a resistor out here, 2.2 kilo ohms. That's going to stay the same. And our 10 kilo ohm resistor from pin 2 over to pin 6. That's going to stay the same. So basically, everything from here over is going to stay the same. Now, what we are going to change though is the input. So we're going to basically switch places with the input and the ground. So I'm going to erase this and this and this. So this one up here, still pin 2. We still have the same numbers 2, 3, 4, 6, and 7. And I'm leaving the minus at the top and the plus at the bottom. That's the standard places for those. So R1 is still what it was, but now it is going to the BNC ground. So I would recommend, now obviously if you want to, you can just take everything out and start all over. But it's going to probably be more convenient if you just make the changes that are necessary. So the R1 it's the one that goes to the BNC ground, and then our input is what goes here to pin 3. So we're keeping it as a sine wave. This is VN, and we're going to put our channel 1 here because that's our input. Move that over a little bit. Okay. So really all we've done is we've switched the signal going in so that it goes into pin 3, and then the ground goes with pin 2. Okay? And you go through, make the same measurements. There's the same questions for drawing the waves. The one thing that is different is that the voltage gain equation is different, and he did another derivation in the book. I decided that I wasn't really that interested in having you to derive those equations, so we're just going to use the equation. So it's a little bit different. But you should get the gains, the observed gains when you do voltage out over voltage in. Those should be really pretty close to what you get with the equations. If they're not quite pretty close, then you might let me know, because mine, I've done it a couple of times and they all seem to turn out okay. Okay, now in part 4 we have an integrating amplifier. So if you think of the word integrating, it's like, what do you think of, or what math class do you think of? And hopefully you think of calculus. Well, we aren't going to do any calculus, but we are going to look at a couple of basic concepts, basic calculus concepts, in just a couple of minutes. But first we need our circuit, okay? So we're going to leave as much of this like it is as we can. What we are going to do though is go back to our original arrangement over here. Pin 3 is going to the BNC ground. And we have our channel, or our pin 2 resistor going here to our input, and our channel 1 here. Now, the thing that's different is that we're going to use our square wave input. Before, on the first 2, we used a sine wave. So then you'll go to the knob and turn to the square wave. I think the square wave is all the way to the right. Okay, so we've switched these back the way they were, changed that to the square wave. We're keeping all of these at 1 kilohertz. It doesn't make a lot of difference if it's a little bit off from 1 kilohertz, but that's just a nice frequency to look at. Okay, so our pin 2 still comes out here to R1. Pin 3 comes here to the BNC ground. Pin 4 is still to -12, pin 7 is to +12, Pin 6 is still over here to our load resistor, to our ground, and with our channel 2 voltage out over here. We also still have R2 up here from pin 2 around to pin 6. Okay, now, the thing that makes it different and the thing that makes it do what it does is we're going to put a capacitor. So that goes up here, and, I'm going to do it. Go ahead and do it this way. I would recommend, I really don't like that. I just do not like that. Okay, I'm going to write it here, 10K, and this is brown, black, orange. And then I can draw my line straight down, which is what I want to do. And that's my capacitor. Okay? So you have actually 3 capacitors, well, you may have more than that. But the little kind of yellow ceramic capacitors, the one that you want to use in this is the 0.22 microfarad. So it's 0.22 microfarad, and that is the 224K. Okay. So then you'll do your input, and then you will look at your output. And it's rather important that you sketch it rather carefully. You're going to get a different kind of looking graph or signal for your output. Now, I guess I sort of have to tell you this because I need to explain number 12 on page 169. We had a square wave input, and what you're going to get for the output is a triangular wave. And so the question is, why in the world would you get that? And how does it do that? Let me go ahead and do this. So, in step 12, you will also notice that the voltage gain, it's not really a gain, it's a diminished voltage. And that actually, the word for that is attenuated. So attenuated means smaller or de-amplified. Now, what will happen is if you put different capacitors in there, you can get various shapes of the triangular wave. And I'll say a little bit more about that in a minute. But the question in number 12 says to explain how a triangular wave can be obtained from a square wave by integrating. So I'm going to explain and show you what and why, okay? So if we start out with a square wave, and I'm not going to have a very big one here, but something like this, and maybe just 2 cycles, okay? Well, the word integrating, what does integrate mean? Well, from the calculus point of view, it means to add areas. So, adding an area under a curve or a graph. So, if we were to start here, how much area is there under this graph? Well, we haven't moved over any, so the area is 0. Okay, so we start there. Now, if I move over to here and find the area, multiplying length by width or width by height, then I will get a number. If I go all the way over to here, I will get twice that number. So it's a linear relationship if I were to find the area from here to all these various places. So what I'm going to end up with is a number under here. So I'm just going to pick a spot. So I would get a triangular wave. Now, when we add areas that are below the axis, those are negative. And this should be the same size as this one. It isn't quite on my graph here, but if I had them plotted exactly, this would be the same as this. If I have a positive number here and a negative number there, then I get back to 0. So this should go back to 0. And I would end up doing the same thing here. So that's how you get a triangular wave, by integrating a square wave. And then there's a question about what do you have to do with this one to get the picture, the graph that you actually get. And it will be a triangular wave, but it won't be quite in this position. So you can tell whether you invert it or leave it the same or move it sideways or move it up or down as to what you have to do with this to get the one that you actually see. Now, there are no other official equations for the gain. Well, there kind of are, but remember this is a capacitor, and you remember from some of the other labs and lessons that the reactance of a capacitor depends on frequency. If you have a low frequency, it has a high reactance. If you have a high frequency, it has a low reactance. So depending on what frequency you have, if you were to change it, you would get this other reactance in parallel with this, and then you get a bunch of different kinds of looking graphs. Okay, so now we want to go to part 5, which is a differentiating amplifier. So you should be able to tell that's going to have something to do with a derivative. And the circuit is very similar. So we have our pin 3. This is a little bit different here, but our pin 3 goes to the ground, 4 goes to -12, 7 goes to +12, 6 goes to our output and our load resistor and ground, and then R2, which is this one, stays the same. Our capacitor is not there though, so we remove it. But you might suspect that since the capacitor was involved with integrating, it should probably be involved with the differentiating circuit, and that's right. So what happens is, instead of this resistor, so we just simply remove that resistor and put a capacitor there. Now, we put a different capacitor there. This is the 0.01 microfarad, which is the 103K. Okay? And then, instead of having a square wave, we start with the triangular wave, which is the middle position, I believe. Right, it's the middle position. So we've taken the capacitor from up there, put it down here, took this resistor out, changed this to a triangular wave, and then we're going to see what we get. So I can kind of tell you that we should have the opposite effect. If we had started with a square wave and got a triangular wave with the integrating circuit, then we should start with a triangular wave and get a square wave when we do a differentiating circuit. And that is what we do end up with. So you'll want to draw things again, draw them carefully and in the right places, so that our square wave, you want it on your graph exactly where it is on the oscilloscope screen. Now, number 12 says to explain how a square wave can be obtained from a triangular wave by differentiating. So again, we're going to use some calculus. Not very much. But if we start with a triangular wave, okay, we'll just do 2 cycles here. And then take the derivative. So from the calculus point of view, taking the derivative is finding the slope. If we have a straight line here, we know that it's slanted upwards, so it has a positive slope. We could actually calculate that slope. It's a positive number all the way from here to here. So I'm going to do this so I can actually get this right. Okay. Now, from here to here, it's a negative slope. It's the same value, same steepness as this one, but it's slanted down, so we will get the same negative value all the way along there. So this needs to go down here and over to there and back up, and we have the same sort of thing. We get a square wave here, and then this has to go back up and then over. Okay? So we've taken our triangular wave and took the derivative of it, and we've ended up with a square wave. Now again, you're going to find that the voltage is attenuated, so this is not as tall as this one, but it does give you a nice square wave. Now, I thought about having you do some more things, but I figure this is actually long enough. But what I think, if you're interested in doing, what will work nicely, and you don't really need to write anything about it unless you just feel like you want to. But the question is, what happens to this square wave when you change this capacitance? So you have actually three capacitors, three of these little ceramic ones. You've got a 0.01, a 0.11, and a 0.22. So you can, if you want to, you just pull this out, put in the other capacitor, and you see what it does to your square wave. And I'm not going to tell you because I think I would like to entice you to actually try this. So you can tell both what happens, or see what happens to the squareness. Does it stay square? Does it get bigger or smaller? Or does the edges get more rounded? And also, you can change the frequency. And if you're going to change the frequency, I would recommend not changing the what I call the dial, but change the knob that has the 1 kilo or 1 kilohertz to get all these ohms and hertz and everything mixed up. You can just turn it down to the 100 or turn it up to the 10K or 100K and see what happens to this square wave when you have the different capacitors and changing the different frequencies. And you could also do that with the previous one and kind of see, as I did, it was kind of interesting to see what actually happens when you have the various frequencies at the various capacitances. Okay, I think that I am actually done. So again, if you have questions, if things aren't looking quite right, or even if you think they're right but you're not sure, please let me know. Now I did send two of the op amps. A couple of them I did check before I sent them. Some of the others I didn't check. But if they start feeling very warm, then turn everything off and take it out and throw that away, because it's not good anymore. And if you happen to end up with two bad ones, let me know right away and I can send you some more, because we have a bunch of those.